This is the lecture of linear algebra, and the textbook is textbook for this course is Introduction to Linear Algebra by Strang. I'm going to use the 6th edition. Okay, and we're going to cover, I think, only 70% of the textbook. Let's start. Vectors, and matrices. So we're going to treat vectors and matrices in all the lectures. And matrices is a kind of an operator, and this is an operator. Operator on the vectors. Okay, and 1.1 sections, vectors and linear combinations. I'll write down the section number and chapter number in all the lectures, and then you can find easily what I am covering. Linear combinations. In this book, sometimes we say just combination. So linear, the word is omitted sometimes, but always what we mean is a linear combination. If I say combination, it just means a linear combination. For example, vectors, and for example, 2, 1, or 4, 3. This is a vector. Yeah, this is an example of vector. Okay. There are 3 definitions. We're not going to be so rigorous on this lecture, but anyway, you're familiar with this definition. Definitions of vectors. Okay. Yeah. When you talk about vectors, a vector is something that has magnitude and direction. So maybe you heard this definition in any high school physics course. So, for example, speed is an example of a scalar because it's just a number, and the velocity is a vector because velocity has a direction. So this velocity and also this velocity is a different one. Yeah. So this is the definition of vector. Something that has magnitude and also a direction. This is a vector. You heard about this definition in any physics course. And another definition of vector is array. So I think, for example, is 1, 2, 3, or just array or list. Yeah, or list. So any in computer science, if you do any programming, is array or list is very important. For example, is 4, 5, 6, and something like that. And this is called column vector. This is column vector because this is a column shape, and this is a row vector, 1, 2, 3, and this is a row vector. So when you define vectors as array, what we mean is that array is the same meaning as the vector. And the third definition of vector is an element. A vector is an element in a vector space. So it's a vector. In this definition, it's a rigorous definition. Usually in high-level mathematics, I think maybe sophomore or junior in university, when you define vector is just an element in a vector space. So anything could be a vector. If we define a vector space, and then the element of any element in a vector space could be a vector. For example, if I define this is V is a vector space, for example, a vector space, and this vector space has elements, a matrix, for example, is a 1, 2, 3, 4, and 3, 4, 5, 6, and 1, 2, 0, 0. And if you can define a vector space in this way, this matrix, this is called matrix. This is 2 by 2 matrix because it has 2 rows and 2 columns. So this is 2 by 2 matrix is an element in a vector space. So in this case, matrix is a vector. So we can, yeah. So this is an abstract definition, and in I think mathematics major you're gonna learn this. But in the engineering course, maybe if you have if you are in an engineering department, maybe you don't learn this. But anyway, this is an abstract definition of vector, and then what is vector space? This is the question. Vector space, you have many, I think 8 or 9 axioms. The really important one is vector space should have 2 properties: closed. Closed under, basically it's just a 1, under plus and the multiplication. And the addition, this is just an addition. And this is scalar multiplication. So we're going to learn 2 operation, which is addition, and the other one is scalar multiplication, and it should be closed. Otherwise, we cannot call this set of V as a vector space. So vector space is a set that satisfies the closedness under addition and scalar multiplication. So we're going to introduce 2 basic operations for vectors. So for the definition of vectors, you can just assume that a vector is just an array. Yeah. And 2 basic operations for vectors is, one is scalar multiplication. For example, if we multiply 3 to vector V, and this is 3, if V vector is 2, 1, column vector, and then we have 6, 3. So direction doesn't change, only we just scale the vector. Okay, and vector addition. This is addition. So we have two basic operations for vectors, addition and scalar multiplication, and v vector. I'm going to put arrow here, but in the textbook, you can see a bold letter, a bold face. So, but to avoid confusion, I'm going to use arrow, but I cannot use arrow every time. So sometimes I just write down a v as a vector, but sometimes I'll write down add arrow to show it's a vector. And 2, 1, 4, 3, 2 vector. Addition of two vectors is 6, 4. So it's very easy because you can do addition. You can do a vector addition just component wise addition. Okay, is vector addition. But if you think vector as something that has magnitude and a direction, so for example, this is v vector, and w is another vector, and then v plus w should be this vector. Okay, and this vector is v plus w vector. And this way of addition we call parallelogram, because we have to, draw the parallelogram, and then the vertex of the parallelogram is the addition of two sides. So this vector, a vector, in addition we have this vector. And as you can see, the direction and also magnitude usually changes. But if we combine addition and scalar multiplication, the only one operation using vectors, it's only one. This is just a linear combination. What is linear combination? Linear combination is that a linear combination of vector v and w is c times v vector plus d times w vector. This is called a linear combination of v and w. But you can see that if d is equal to 0, this is just what we have, just a c times v vector. This is just multiplication. Yeah. A scalar multiplication. And if c and d is equal to 1, what we have is v times v plus w. This is addition. Okay, addition of vectors. So if we have linear combination, so linear combination could be addition, or it could be a scalar multiplication. So it's a kind of a combined operation. So if we have, so we can check. So in the proof, any mathematical proof, sometimes you use addition and scalar multiplication, and sometimes if you use a linear combination, you can shorten your proof easily. But anyway, we have basically one operation for vectors, and that's called a linear combination. This is an example of a linear combination. 5 times v minus 2 times w vector. So we assume that v vector is 2, 1, and w vector is 4, 3. And what we get is tan 5 minus 8, 6. So the result is 2 minus 1. Yeah, this is a result of this linear combination. Right now, the two key questions are given two vectors, v and w, c times v plus d times w can fill a plane R2. Okay, that means it could be the whole space. What I mean is that so we can think about the set C times V plus D times W. This is the linear combination, and this is the set, and we find C and D could be any real number. And right now this is a set. Okay, this is a set. And the question is whether this set is equal to R2 space. I mean, the plane. This is a question. And the other question is on the next page. And in other words, so this question is, we can say the vector v and w could be generators of R2, and so we can say this question could span R2. So this is the same question. So whether it could fill, it could generate, any vector in R2 using a linear combination. Whether we can generate all the vectors in R2. And this is a key question. And the second question is given given v vector and w vector and b vector, can we find the coefficient c and d such that CV and D times W is equal to B. And also we can generalize these questions to n dimension. So we're going to cover this question in chapter 1. To answer these questions, we first have to know the matrix column vector multiplication method. So when we multiply the matrix, the method is 1, 2, 3. For example, 4, 5, 6, 7, 8, 9. 1, 0, 0. We have to use a dot product. I think we cover dot product later, but I think we need to cover this. So, for example, a dot product is simply 1, 4, 7 and 1 0 0. We have a big dot here. This is called dot product. What we have is scalar, so 1 times 1 and 4 times 0 and 7 times 0. So what we have is just 1. And this is dot product. This is when you have two vectors, we can define a dot product. Another example is, for example, 1 4 7 and then 2 3 5. And the dot product between two vectors is 1 times 2 plus 4 times 3 plus 7 times 5. Okay, so it's 2 plus 12 plus 35. So this is called dot product. When we have a dot product, when you do dot product, what we have is scalar. Okay, so we have scalar. Two vector, dot product, what we have is a scalar. So in that way, we can multiply a matrix and a vector. Okay, so the method is, you see this is a row, and I think we should erase this. And the first component of the vector is 1 times 1 plus 4 times 0 plus 7 times 0. Okay, so this is the first component. And the second component is also a dot product. So I think we're going to use the second row is just a row vector. And the second component of the output vector is 2 times 1 plus 5 times 0 and 8 times 0. Okay, and the third component, we have to use a third row, 3 times 1 plus 6 times 0 plus 9 times 0. So using dot products, 3 dot products, we have a column vector. Okay, so this is a way how to multiply a matrix to column vector. And then we need to show the size. This is a 3 by 3 matrix, and this is this is vector, but we can think of as a matrix anyway. So this is 3 rows and 1 column. So this is 3 by 1. And to define a multiplication between matrix, this one and this one should be equal. Okay, otherwise we cannot define any multiplication. And then result is the 3 by 1. Okay, so this is a 3 by 1. This is just a vector. Okay, so this is a vector, 3 by 1 vector, and this is 3 by 1 vector. Okay, so this is a way of multiplication of matrix and column vector. But there's another way of multiply a matrix and column vector. This is a column way. So you divide a matrix into 3 columns in this example. So we have 3 columns, 1 2 3, and the second column is 4 5 6, and the third column is 7 8 9. Okay, and the weight. So what we have is just a linear combination. So the this first component, 1, is a weight for the first column, and the second component of the vector is the weight for the coefficient. A weight or coefficient is the same word. A weight of the second column, and the third is the weight for the third column. So what we have is so we see the vector is just a 1 0 0. That means we're gonna erase this part and we're gonna erase this part. Okay, so this is because the weight is 0, so that part is gone. So what we have is just 1 2 3. Okay, so this is easy. And another example could be 1 2 3 4 5 6 and 7 8 9, for example, no, no. Example, if the vector is 1, 1, 0, so what we have is the weight for this column is 1, okay? So, and then the weight for this column is 1, and this is 0. So that means we're not gonna use that column. So the answer is 5, 7, and 9. Okay, so it's just the addition of the first column and the second column. So in general, what we have, if the is a V1 column, this is a vertical bar, is just a column vector. Okay, so this column V2. Maybe in general we can think of n columns. Okay, so we have n columns. We have a matrix that has n columns. Okay, so and then the vector consists of x1, x2, and so on, xn. Okay, and what we have is x1 v1 vector plus x2 v2 plus and so on xn vn. Okay, so what is that? This is just a linear combination of the vectors v1 and up to a vn. Okay, so you can write down a linear combination of vectors this way, or just you can use a matrix multiplication. So this matrix multiplication between matrix and vector is just the linear combination of column vectors. Okay, and this is the key question, the second key question. Given ax is equal to b, what is x vector? This is called a system of equation. System of equations. Okay, and so A is just column vectors, set of column vectors. And we have n columns in A, and this is matrix A. And x vector is just x1, x2, and so on, xn. And then this is b vector. So we want to find the coefficient of the this equation. This is called a system of equation. We're going to tackle whether in what case the solution exists, and then talks about the uniqueness of the solution. And we're going to cover existence, and uniqueness of the solution. As an example, we're going to solve two equations. So the two equation is 2c plus 2d is equal to 8, and c minus d is equal to 2. So you can write this system of equations like this, or you can write this system of equation like this. Okay, so because if we use a matrix notation, and then we can write this equation like 2 minus 1 and c d and a2. Okay, so if we use matrix, and then we can write down this equation like this, and you see that this is the first column, and then so this is connected with the weight c, and 2 minus 1 is the second column of the matrix, and then the weight for this second column is D. Okay, so we have this equation. And so how to solve it? So we divide this equation by 2. What we have, C plus D is equal to 4. And the other equation was C minus D is equal to 2. And then we subtract. And the left-hand side is 2D. And then right-hand side is D. And D is equal to 1. And then we just substitute this value to any equation, and then we can find that C is equal to 3. This process is called elimination. Elimination of the first term of C term. Okay, C. So this is called elimination. Because when we have this equation is complex because there's a coupling. Okay, so C and D, there's a coupling. So that's why it's not easy to solve. So what we do is elimination of one term. So what we have is a 2D is equal to D. You can see that there is only one variable, D. So the coupling is gone. Okay, so coupling is gone by elimination. You can say this is just elimination, or just it's called Gaussian elimination, because Gauss developed this, so we can say this is Gaussian elimination, or just you can say this is elimination. So in this way we found the solution. So this value is the weight of the vectors that satisfy the equation. So we can write this as 3 times 2, 1 vector plus 1 times 2 minus 1 vector is equal to 8 and 2. Okay. Oh, so if you want to use a matrix notation, and then we can write this as this one. 1 minus 1 and 3, 1. This is 8, 2. Okay, so this is A matrix, and this is X vector, and we're going to use the B vector for the right hand side. The question is, can elimination fail? The answer is yes. See this example. When V is 1, 2, and the vector W is 3, 6, and B is equal to 1, 6. Okay? And so the equation in matrix format we can write down in this way. 1, 0. So we're gonna so we can do elimination in this stage. Okay, we can do that right away. And so what we do for the elimination, we just multiply minus 2, and then add to the second row. Okay, so we for the this row and this row, and we multiply minus 2, and then add to the second row. Okay, so So this part doesn't change, okay? And then the 2 is gone, okay? Because so this was eliminated, and this is 0. But the problem is 6 is also gone, because minus 2 times 3 is equal to minus 6, so this is gone also. And so 1 times minus 2, okay, so minus 2, multiply minus 2, we get is 0 plus minus 2, so what we have is minus 2. So the first equation is just the c plus 3d is 1. This is no problem. But the second equation is 0 times c plus 0 times d is equal to minus 2. Okay, so that this equation is 0 is equal to minus 2. So in this case, there is no, so this is not true, so there is no solution. Okay, so the solution does not exist for this system of equations. When we see this equation as a row way, I mean row by row, we don't have any intuitive explanation of the fail of elimination. I mean, row way, we can write this equation as, I think this is 2 and this is 3. And if you write the equation row by row, c plus 3d is 1, and 2c plus 6d is 0. But in column way, what we see is that c and d times 3, 6 is equal to 1, 0. Now we can see 1, 2 vector and the vector 3, 6 are on the same line, because this is the line, and this line is y is equal to 2x, and 1, 2 vector and 3, 6 vector are all in the same line. So, but we can see that 1, 0 is not on the line. It's not on the line. It's not on the line. On the line, the line equation is y is equal to 2x. Okay, so that's why. So the left-hand side is the linear combination of 1, 2, and 3, 6, but they are all in the same line. So the linear combination of these two vectors, this should be is on the line, but 1, 0 is not on the line. So we cannot find any weight that satisfies this equation. So in column way, we can explain why this equation fails. The two vectors 1, 2, and 3, 6, they are linearly dependent, because 3, 6 is 3 times 1, 2. Linearly dependent means that one of the vectors could be a linear combination of the other vectors. So in general, we have V1 and V2 and so on, Vn. If vi, any vector vi is a linear combination of the other vectors. This is very important definition, so I'll write down everything. Other vectors. Then v1 up to vn are linearly dependent. So that means one vector could be generated with using the other vectors. If two vectors they belong to the plane, the R2 plane, if they are linearly independent, this equation CV plus dW is equal to B has a solution. Has a solution CD. Okay. The reason is that a linear combination of V and W can fill R2. So that's why we have a solution. I mean, this time V and W, and we have this equation CD and is equal to B, but we assume that this V vector and W vector are linearly independent. That means span of V vector and W vector, maybe we can use the set notation, and this is our 2 right now. This is our 2, and that's why we can have solution. The span, so the definition of the span, this one is all the elements CV, maybe C1 or C2, W, and C1 and C2 in R. Okay, this is the definition of the span. Okay, when I write a span, the definition of the span is the all the elements, all the vectors are generated by V vector and W vector. In this case, we write this way. Okay, so B, any vector is in R2, but we can generate any vector in this case if V and W are linearly independent. So we can generate any vector. So for arbitrary vector B, we can find the weight CD. Okay. So in this case, we can say we can find the solution. I mean, the solution exists. Before we move on, I'm gonna teach you how to prove. So how to prove any equality. So in any mathematics course, you could sometimes you meet this questions, like you have to prove whether you have to prove that A is equal to B. Okay, this type. Prove that. Prove that. Prove that A is equal to B. When I mark the exam, in many cases, I I saw this kind of answers. Some student answer like this way. A is equal to, they start with this line. This is the question. This is the question. So question. And the student answer, sometimes they show their proof, and then they show A is equal to B, and something is equal to something, and blah 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 blah, and then finally they reach the point like 0 is equal to 0, and then they say this is the end of the proof. When you write in this way, you'll get a 0 point. Okay, so the right answer is that the right answer should start like you have to calculate A minus B. Okay, and then you start with this equation, and then write blah blah, and then is equal to blah blah, and then finally you're gonna get 0 here, and then you can write the end of the proof. Okay, so the calculation, needed calculation, would be very similar, but this is the correct answer. Okay, correct, and then this is incorrect. Okay, because the first answer assume that you use that A is equal to B. Okay, so but A is equal to B, you need to prove that. So you cannot assume A is equal to B. So this one could not be the first line. Okay, so this is typical incorrect answer. And so the second, the right answer, you see that when you start the proof, you don't know whether A is equal to B. Of course, you know that it should be 0 here, because otherwise the question is wrong. But anyway, when you start the proof, you need to pretend that you don't know whether A is equal to B. Okay, so you need to show at this stage you have to show some kind of fake surprise. Okay, so finally we got 0, so that's the end of proof. Okay, so you have to be very careful. I mean, this is the typical incorrect answer. I saw this kind of answers many times. Well, if you have many common terms, maybe you could try A divided by B. Okay, but well, it's basically the same concept. You just keep going, and then you're gonna find 1, and then you can write that end of the proof, because A divided by B is equal to 1, and then you can say A is equal to B. Okay, so that's you can the first line could be A minus B, or first line could be A divided by B, so whatever will be fine. How about this case? Well, there's another method. I mean, third method. You need to prove that. Yeah, it's the same question. The question is prove that A is equal to B. There's another way to prove that. First, you prove that A is greater than or equal to B, and second one is you need to prove that A is less than or equal to B. Okay, if you prove this one and this one, then you can say that A is equal to B. Okay. But of course, when you want to prove that A is greater than or equal to B, what you should do is that you have to start with A minus B. Okay. And then you can write a blah blah and is equal to blah blah, and finally you can write this thing. Okay, so greater than or equal to 0, and then so this is the end of the proof. Okay, and then and similarly, when you need to prove that A is less than or equal to B, you have to start your proof with this line, like A minus B is equal to blah blah, and then blah blah, and then finally you have to write in this way. Okay, less than or equal to 0, and then so this is the end of proof that you can say that in this case, I mean, if you prove this, and then you can say that A is less than or equal to B, and then combine this one and number 1 and number 2, and you can write that A is equal to B. Okay. And another question is, you need to prove A is equal to B, but in this problem, A and B are set. Okay, a set. So in this case, so A minus B is doesn't work usually, because a set theory, well, you can define the difference of the set, but is not so good for proving that the set A is equal to set B. So I cannot recommend this way, but there's a hint. Yeah, you already know. So you need to prove that A belongs to B, and B is in A. Okay, I mean, well, A is not an element. Maybe the right word is A is a subset of B, and B is a subset of A. If you prove that, if you prove these two facts, and then the proof is done. Okay, so, but how to prove this one? I mean, subset A is a subset of B. How to prove that? The proof should start that the first line should be suppose X belongs to A. Okay, so I'm going to erase this part right now for making space, and then you can blah 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 blah. Okay, and the last line should be X is in set B. Okay, so A is a subset of B. Okay, so this is the only way. Okay, if you need to prove that A is a subset of B, you have to start with this line. Suppose X belongs to A. Okay, this should be the first line. This is the end of the proof. Okay, what you need to do is just fill out this fill out in the middle. But usually it's very easy, because you know the start, and then you know the end, and then you just fill out in the middle, and then your proof is done. So similarly, if you need to prove that B is a subset of A, and then the first line should be suppose X is in B. Okay, and then blah blah blah, and then finally you can write that X is in set A. Okay, so So therefore, B is a subset of A. Okay. Using this fact, A is a subset of B and B is a subset of A. If you prove both facts, and then we can say set A is equal to set B. Okay. So this is also very important. What I mean is that when I make a question that to students that you need to prove this something, and then the students just write anything. They want to write everything they already know, but it's wrong, usually wrong. So you get 0 points even if you write whole pages or 2 or 3 pages. You get a 0 point. Okay. What I mean is that if you need to prove that, and then the first line is just this one. There is no other way. Okay. Another type of this is not about equality. Maybe so it's a wrong title because I talked about equality. I mean, you need to prove this kind of thing. So if-then structure. If B is true, and then you need to prove Q is true. Okay. In many cases, you think about this one. Okay. So negation of conclusion, and then you prove that the assumption is wrong. Okay. So it's an indirect proof. It's called contraposition. So you can prove any if-then structure, and then you just negate the conclusion, and then you can prove that. Sometimes you can prove easily that P is not true. So you can prove that if P is true, and then Q is true, and then or you can prove that if Q is false, and then P is false. But in many problems, you don't have this kind of simple structure. So in many cases, you have a lot of assumptions, P1 and P2, and for example, Pn. And then you need to prove that if all the conditions are met, you need to prove that Q is true. What you're going to do? So if you do just a contraposition, you need to prove that if Q is not true, P1 is false, or P2 is false, or and so on. Or Pn is false. Okay, so this is contraposition. Okay, so this is a contraposition. Are you gonna use this method? Because you see, this is so complex. Okay, so you don't want to use that. So what is the best way? Best way is that you think about P1 and P2 and P3 and so on, and Pn, and then you think adding not Q. Okay, so you assume that this one is true. Okay, so you think well, the end conditions are already mentioned here, the end condition, but you add Q is false. Okay, so not Q, you include not Q in the assumption, and then you just derive any equation logically. Okay, then what you're gonna find that something strange. For example, you're gonna meet 1 is equal to 0, or just -1 is equal to 2, something like that, and then in that case, and then you can immediately say this is the end of the proof. Okay, so just adding this not Q, and then you're gonna find something weird, something strange, and then you can immediately say this one is true. Okay, this one is true. So this technique is used many times, but I think students sometimes they don't know this technique. So I covered in this lecture. Now we'll consider vectors in 3 dimensions. For example, V is equal to 2, 3, 1, column vector, and W is a column vector 1, 1, 0. The question is, can CV plus D times W fill all 3 space? No, because we have only 2 vectors, okay? So if we have this 3 vector, 1, 0, 0, 0, 1, 0, and 0, 0, 1, what will happen? For example, if we have a linear combination like this, C times I plus D times J, and E times K, then we can have CDE. But CDE is arbitrary number, so that's why using this 3 vectors, we can generate any vector in all 3. If we make a matrix using this 3 vectors, 1, 0, 0, 0, 1, 0, this is K, and then 0, 0, 1, this 0, 0, 1 is K, but if we make this matrix, we will call this identity matrix. Because if we multiply identity matrix to any vector, we're going to have the same vector. So it doesn't change the vector. The identity matrix does not change any vector when you multiply this for any vector, for any vector V. So we will call this matrix as identity matrix. This is the end of section 1.1.